Thank you. Can you see my screen here?
Yes, we can see.
Oh, good. Then I will start. Hello, everyone. My name is Hui Sun. I'm from National Astronomical Observatory, Chinese Academy of Sciences. It's very interesting. It's very nice of the organization to invite me here to give this talk. And my talk is on the X-ray transients powered by Magnetar spin down from binary neutron star merger. And so since the detection of the GW170817, which is the first GW event, gravitational wave event from binary neutron star merger, and the only event that with the electromagnetic counterpart detected with GW signals. So as you can see here is the GW signal, and the above figures show counted electromagnetic counterparts in gamma ray band, and also on the right you see the optical and infrared light curves, and also a later multi-wavelength light curves at the right panel. So the multi-messenger detection of one single event, especially on the binary neutron star merger event, help determine that the short gamma ray bursts are from the binary neutron star mergers. Also, they can provide the distance location detections as well as the host galaxy, and the jet physics can be further employed with the more detailed information of the observations as well as the ejector properties. Here I will show a more general picture for you if you can see on the slide that if the case is that there are two neutron star merger, and there might be a hypermassive neutron star or a black hole left, and then there will be a jet propagating into the circuminterstellar medium, and also the blue and red direction show the ejector, which also was released during the merger, and the multi-messenger messages are emitted, like the gamma ray bursts are seen actually with an observing angle of around 20 to 30 degrees. It might just be the direction here. And also there are bright optical and infrared emission by the so-called kinonova. And also there might be some radio and X-ray and radio afterglow powered by the jet. So whether it is true the merger product of the binary neutron star are black holes or hypermassive neutron star, or some cases it depends. Actually, it depends on the neutron star equation of state and the mass of the merger remnant. Generally speaking, if we have the two neutron star merge, the mass of the remnant here we use the MS denote. It is the gravitational mass of the merger remnant. And we have to compare it with the M12, which is the maximum mass for non-rotating neutron star. And another mass called Mmax is the maximum mass for rotating neutron star. It is very easy to understand that if the neutron star rotates, it has a more it can survive within with a more maximum mass. So if we compare the gravitational mass of the merger remnant with these two masses, then in case it is very large, the remnant is very massive, then it collapses into a black hole directly. And if not, it is very small, then it does not collapse at all. It can lead to a stable neutron star. In some cases, between the when the mass is between the M12 and M mass, They can survive as a supermassive neutron star or a hypermassive neutron star and then collapse into a black hole. There are some signatures in electromagnetic waves that can be used to distinguish whether a black hole or a supermassive hypermassive neutron star or a stable neutron star left. And in present, the neutron star equation of states of just too many models to describe them as the mass and the radius relation of the neutron star. And gravitational wave detections are a very effective way just to help distinguish which equation of state work. And another way is when the equation of state is settled with the distribution of the neutron star mass, we can determine how much fraction of each remnant. The remnant are just the black holes or stable neutron stars or just supermassive neutron star or hypermassive neutron star. And for a case, for example, if we use this equation of state and a galactic neutron star mass distribution, the merger can leave around 40% of black hole or 30% of stable neutron star. And the prompt black hole include the hypermassive neutron star. And 30% of the remnants can be supermassive neutron star. That's just example, and the cases are more complicated given different equations of state. When we compare the electromagnetic counterpart for black hole merger, black hole remnant and a massive neutron star, or just called the Magnetar remnant, the observation or observational signatures are quite different, or there are some similarities and some differences. Generally, there are jets in the direction of the polar direction and produce the bright gamma ray burst, which is similar case for a Magnetar remnant. And also in the equatorial area, there will be kinonovae, which is similar as what we have seen from the GW17017. And the difference lies here in case of a Magnetar left, there will be a bright X-ray emission. The X-ray emission is powered by the dissipation of the magnetic wind. So it is a very direct or a unique role to differentiate the post-merger remnants. And the X-ray emissions are more like isotropic. In in contrary, these SGRBs are more like beamed, and they just have a very narrow observation angle if the observer has to be just face to the jet direction, while the X-ray emission here labeled by the blue arrows, they are more like isotropic and have a much larger event rate density compared with the short GRBs. And do we have some observations here on the X-ray emission? Yes, but mostly they are in the observations embedded in the short GRBs because this fast X-ray transients actually need the wide field of view of the telescopes, and just with the BET, which is the on board of Swift, is the wider field of view gamma ray detectors. We have seen a lot of X-ray emissions, which shown here as called the plateau emission, which can be regarded as the X-ray emission powered by Magnetar. And the light curves can be more specifically, the light curves can be more we can expect more types of shapes in the light curves, like the plateau case in the beginning, and the decay as T2-2, which is the standard light curve predicted by the Magnetar dissipation And in some cases, there is a T2 minus 1 to T2 minus 2 transform, which is because the magnetar spin down can also power a gravitational wave emission, and this emission can, in some cases, be dominant at the beginning, and then the EM emissions will, or the dipole emission will dominate later. And in some cases, you can see a light curve in the C case, which the plateau emerged at the beginning and just decline very fast. That is because the magnetar will collapse into a black hole. Then the central engine stop powering this bright X-ray emission, and the light curve will show just sharp decay. So this short GRB data are consistent with the hypothesis that the Person merger product of a neutron star merger can be a supermassive neutron star. And this existence of such a long-lived Person merger product can open some interesting prospects in the multi-messenger area. However, these GRB-related X-ray transients are rare due to the beaming constraint of the GRBs. We expect that more isotropic X-ray emissions can be detected just off the short GRB observing angle. So we, in 2017, we published a paper which just to describe what the X-ray light curves can be. By that time, we don't have one single event of the short GRB-less X-ray transient. So the predictions can be used to identify the observations. In some cases, in the jet direction, the X-ray emission will be similar to those observed in the short GRB X-ray afterglows, which here shows a flat X-ray emission and decline, and maybe in some case it will collapse. There will be a sharp decline. And in some cases, there is an ejector. It will absorb the X-ray emission and emit when the ejector is optically thin. So the X-ray emission at the beginning will not diffuse, and it is shown in the black panels here as the light curve will emerge later. It is the time when the ejector is optically thin, and it will emerge as the plateau phase or at the decline phase. It depends on the magnetar and the properties of the ejector. In some cases in between, there is free zone where there is no ejector and no jet zones. This X-ray emission just shown here as which is similar to the jet zone, but there is no short GRB accompanying. Interesting to say that in 2019, we have a first case called the short GRB-less X-ray transient, which is in collaborated with one of our collaborators, and we find that there is in Chandra deep field south survey, which is very highly sensitive exposed observations with 7 million exposure in just an area of 484 arcminutes square. And in this region, we find a case called CDF-S XT2. The reason is that there is another transient I will describe later called CDF XT1. They name the interesting unknown X-ray transient as the XT1, XT2, just following the X-ray transient names. And when they find this one, they call the XT2, and the light curves it shows similar properties to those observed in the short GRB X-ray afterglows with the plateau signatures. You can see at the first 2 kilosecond, the light curve is very flat, and the later decline as T2 minus 2 slope, and this is very identity to the Magnetar powered X-ray emissions. And the host galaxy is shown that this one is at the outskirt of this host galaxy, which is very consistent with the merger scenario. As you can imagine, the merger takes a very long time, and normally the short GRB, the host galaxies of short GRBs shows a very less star forming rate, and the short GRBs, the allocation of the short GRBs or the binary neutron star merger is generated at the outside of the host galaxy. Another fast X-ray transient is called the CDF-S XT1, which I just mentioned. This one, the light curve is different. It does not show a plateau. It shows a fast rise and a generally slow decay. And if we compare, so the redshift of this one is a photometric redshift, which is around 2.23. And this author about Franz Bauer, they give a general redshift range even from 0.03 to 2.2. The light curve is at this red shadowed region. If we compare to the other known transients, fast X-ray transients like shock breakout or TDEs or short GRB afterglows, they are just show no similarities. So this one stay unknown for a while on its physical origins. But in 2009, we published a paper which is trying to explain both the XT1 and XT2 in a case of a Magnetar as a merger remnant from binary neutron star. And in this plot, you can see that the XT2 is consistent with the published paper of the observation published paper, and it is just powered by this magnetic wind in the free zone, and the luminosity is just shown as T2 flat at the beginning and later decline as T2 minus 2, while the XT1 actually can be explained as the X-ray emissions from the trapped zone, as the ejector absorbed the blocked the X-ray emission at the beginning, and it declined, it diffused out later. So there will be a tau here, which measures the optical depth of the ejector. So that's why the X-ray emission emerge later, and this does not show the plateau case. We fit both the CDF-XT1 and the CDF-S XT2 with the within the Magnetar model, and it shows a very well-fitted light curve result. And the parameters are listed here. The parameters including the magnetic field of the Magnetar and the initial spin period. And this is the efficiency of transforming the spin down luminosity into the observed X-ray emission. And the ejector mass can be measured for the case in trapped zone, that is the XT1. And so these parameters are consistent with the other parameters measured by the short GRB plateau, short GRB plateaus, which are labeled by either the origin case or the blue case. They just depend on different study of the study of different groups. And here labeled the star labels the result for the XT1 and XT2. They are following in the very reasonable range in the BP distribution. Also, we compare the host galaxy properties with the short GRBs and long GRBs in case if the CDF XT1 and XT2 are from the Magnetar case, they might be identical with the short GRB case. And so we labeled here the XT2 are more like in the middle of the XT2 of the short GRB distribution, which is marked in blue, and the red XT1 is falling at the end of the short GRBs. It's still consistent, does not, we cannot exclude that it also can be identity to these long GRBs, just have to compare it with them in this distribution and then find some consistency at first. We also evaluate the rate for the XT1 and XT2. And this plot is shown as when the GW170817 is detected, we plot a figure as the rate versus luminosity, and the black dots shown the short GRB's rate distribution. And when this GW170817 is detected, the rate is estimated to be around 200 per cubic parsec per year, which is due to its very low luminosity and possibly wide observing angles, while the blue is showing the rate for the binary neutron star merger is around 1,500-ish per cubic parsec per year. And the rate estimated for the XT1 and XT2 is generally consistent with the GW event, with the binary neutron star merger rate from the GW event. That is to say, there a fair amount of binary neutron star merger can leave a magnetar as a product, which can in turn impose constraint on the equation of state of the neutron star. That is to say, the M12 cannot be too small. So the future prospect, as we can see that the fast X-ray transients require very large field of view of the telescopes. So far, we have followed the two discoveries. Another paper, Young, in 2009, they searched the Chandra survey. Even though the Chandra has very small field of view, they have been working so far for a really long time. And they conclude that there might be 13, they find 13 fast X-ray transients, including XT1 and XT2, even though the rest 11 is belong to stellar objects. But they imply a rate that there may be around 15-ish transients hidden in existing Chandra algebra observations, which relies for future searching out algorithm to find them out. While for future, we expect the wide field of view telescopes like the Chinese Einstein probe satellite, which will have a field of view of 1/10 of the sky. That is around 360 square degrees. Sorry, and this is a very effective telescope to catch these fast X-ray transients. If you want to have more information, you can go through the website. And also we can expect the joint LIGO and Virgo and the Calgary, and also in optical band, to detect the so-called kilonova or merger nova by LSST and other optical telescopes to do the multi-messenger and multi-wavelength detections. Here give a summary of this talk. We propose a unified binary neutron star magnetar model to fit the two X-ray transients CDF-S XT1 and XT2, and using these fitted parameters, we can the fitted parameters can be consistent with the SGRB X-ray plateau observations, and the event rate density of two events are consistent with the binary neutron star mergers. Okay, we expect the future wide field telescope to find more transients to just to test the models. Thank you.
Thank you, Dr. Huising, for your wonderful presentation. Yeah, indeed, it's a wonderful presentation, and I'll leave some time here. Any questions from anyone? I think today we have very calm listeners today. So, any questions from any?
I have a question. Like from the gravitational point of view, do you have any other candidates from the last run of the LIGO? Because you have like a lot of new events, and
yes.
Do you have something among them?
I have no slides to show, but the majority detections are the gravitational wave signals from binary black hole mergers. There are several cases, several new cases for like I'm not sure, it's less 10 cases for binary neutron star mergers, but we don't have another electromagnetic part observations for sure.
Okay.
If we conclude the total number of the gravitational wave signature detections around 50 events, I guess, in total.